Its name is Cassini-Huygens. On October 15, 1997, it sailed out from the port of Earth on a 7-year, 2-billion-mile odyssey to the outer solar system. The size of a school bus, with a total weight of over 12,000 pounds and an array of 18 packages of scientific instruments, Cassini-Huygens represents the combined effort of scientists and engineers in 18 countries and is one of the largest, heaviest, and most sophisticated interplanetary spacecraft ever launched. Its destination? One of the most intriguing objects in the solar system. A world of unparalleled beauty and the undisputed Lord of the Rings, Saturn. For Cassini, the road to Saturn is both long and winding. A complex but clever routing, carefully designed to not exceed the limited fuel available and, at the same time, take advantage of some extra sightseeing and science along the way. In what amounts to going the wrong way first, Cassini leaves Earth and heads inward, toward the Sun, for a rendezvous with our neighbor world, Venus. But this move is intentional, and only the first step in a calculated series of what scientists and engineers call gravity assists. As it swings close, Venus's gravity is used to tug on Cassini and change its speed and direction in a very exact way. For after an engine burn known as the deep space maneuver, the spacecraft loops back for a second encounter with Venus. But the flight path is different this time, different enough to direct Cassini back toward Earth. Scientists now use this flight past Earth instead of the initial launch from Earth to toss the spacecraft outward, away from the Sun. And so Cassini finally sails out across the orbit of Mars, through the asteroid belt, and on to giant Jupiter. During the late 1990s, a spacecraft named Galileo arrived here, went into orbit around Jupiter, and provided unprecedented reconnaissance of the planet and many of its satellites. Now, in what becomes known as the Millennium Flyby, Cassini adds its cameras and scientific instruments to the effort. Working in tandem, Cassini and Galileo map Jupiter's immense magnetic field in 3 dimensions as high-energy particles, streaming from the distant Sun, buffet the field and continually reshape its outer boundaries. Some of the particles, along with others from Jupiter's volcanic moon, Io, are channeled along spiraling paths down toward the planet's magnetic poles. There, they collide with Jupiter's upper atmosphere and set vast regions aglow with shimmering displays of the northern and southern lights. In addition, the 2 spacecraft send back a flood of other data, including dazzling images. But how do data and images get from spacecraft such as Cassini back to scientists, hundreds of millions or even billions of miles away on Earth? In California's Mojave Desert, a giant dish-shaped antenna 230 feet in diameter stands ready to perform the task. Together with two other sets of super-sensitive radio antennas near Madrid, Spain, and Canberra, Australia, they comprise the components of NASA's Deep Space Network, or DSN. As the Earth spins in space, the antennas of one DSN complex after another are strategically positioned to keep a nearly constant vigil on a distant spacecraft such as Cassini. The Deep Space Network provides data on the spacecraft's speed and distance. But its main purpose is to serve as a two-way link, allowing scientists and engineers to send instructions to the spacecraft and also receive data, including images from the spacecraft back on Earth. All this information is sent to Earth as strings of ones and zeros, riding the backs of radio waves transmitted from Cassini's antennas. High-speed computers at NASA's Jet Propulsion Laboratory in Pasadena, California, are linked to the DSN and transform these streams of numbers into meaningful information. In the case of images, numbers become dots or pixels in various shades of gray that are then arranged row by row into rectangular pictures. 3 or more such black and white images, taken through different colored filters, can then be combined to create an image in color. And sequences of such images can be strung together to add dramatic time-lapse motion to make phenomena like Jupiter's enormous dynamic cloud systems come to life. The task is not dissimilar from what your home computer does in converting numerical data into pictures you may get with email or via a TV satellite dish. But NASA's Deep Space Network antennas are far more sensitive. They need to be, for the typical signal transmitted from a spacecraft such as Cassini is so diluted by the time it reaches Earth, it can be 20 billion times weaker than the power needed to run a single digital wristwatch. The Deep Space Network, plucking whispers from the sky and over the years providing a vital link to Cassini and NASA's many other robot explorers across the solar system. As winter melts into spring 2001 back on Earth, Cassini wraps up its brief sojourn at Jupiter. It has been 3 years and 3 months since its launch from Earth. Now, the final gravity assist from Jupiter is all that is needed to set the stage for the main event, Cassini's encounter with Saturn and its entourage of fascinating satellites. Mid-June 2004, Cassini finally reaches the domain of Saturn. Now, the main work begins. From this great distance, even traveling at the speed of light, Radio signals to and from the spacecraft will take nearly 3 hours to make a round-trip journey. So engineers have built the spacecraft smart to largely think for itself, using carefully pre-planned instructions and contingencies in case of emergencies. Things are about to start happening so fast, Cassini will largely be on its own. "19 days before Cassini officially arrives at Saturn, it encounters the largest of the planet's outer satellites, Phoebe. The images are wonderfully clear and reveal what may be a denizen from the far reaches of the outer solar system that has been captured by Saturn. Such objects have been described by some as dirty icebergs. Indeed, several of Phoebe's craters lend evidence to this scenario, for they show darker surface material which has slid down the walls of craters to reveal bright ice underneath. Cassini races toward its rendezvous with Saturn, drawn by the ringed giant's strong gravitational field. As Cassini plunges onward, its speed approaches 50,000 miles per hour, fast enough to fly coast to coast across the United States in 3 minutes. A moment of truth has arrived, a hold your breath moment, upon which the entire rest of the mission hangs, for at this speed, Cassini is moving too fast and would simply fly past Saturn. The spacecraft streaks inward, skirting just above the rings, and then for nearly 100 minutes, Cassini's main engine fires in just the right way to change the spacecraft's speed by 1,300 miles per hour and allow it to drop into orbit around Saturn. Cassini's instruments take advantage of this closest approach to scrutinize the rings and monitor the innermost regions of the planet's magnetic field. For the next 6 months, Cassini completes 3 carefully executed orbits of Saturn as images and other data stream toward Earth. During these 3 orbits, engineers also painstakingly adjust Cassini's speed and prepare the spacecraft for the next critical part of the mission. Now it is time for Cassini's piggybacking Huygens probe to take center stage. The product of the European Space Agency, Huygens' mission is to detach from Cassini, descend into the atmosphere of Saturn's largest satellite, Titan, and actually land on its surface. A final systems check, and then "4 hours before Huygens encounters Titan's upper atmosphere, a wake-up call sounds, and Huygens' array of instruments comes alive. Larger than the planets Mercury and Pluto, Titan is one of the most intriguing satellites in the solar system. It has a substantial atmosphere, a thick, smoggy shroud of an atmosphere. But cameras on Cassini begin to see through the haze, to reveal tantalizing light and dark features below. With Huygens on final approach, the landing zone is narrowed. Batteries alone will power the probe through the next few critical hours, the first epic landing on the moon of another planet. The descent phase has begun, as Huygens slams into Titan's upper atmosphere at nearly 14,000 miles per hour. Over the next 3 minutes, temperatures immediately in front of Huygens' heat shield will soar from 300 degrees below zero to over 21,000 degrees Fahrenheit, twice the surface temperature of the Sun. In the same 3 minutes, atmospheric drag also breaks the probe's speed from nearly 14,000 miles per hour to less than 900. At 1.5 times the speed of sound, a pilot chute is released, pulling off Huygens' aft cover. Almost immediately, the probe's main parachute unfurls. We are 110 miles from the surface. Within 30 seconds, Huygens has slowed to little over half the speed of sound. The heat shield has done its work and is jettisoned. For the next 15 minutes, the probe descends under its main chute as initial scientific measurements begin. High above, Cassini collects the data transmitted by Huygens and stands ready to relay it to Earth. Finally, a smaller drogue chute takes over. Altitude, 85 miles. For the next 2.25 hours, as it continues its descent toward the surface, Huygens' instruments will be busy. Winds build to 250 miles per hour as Huygens sniffs Titan's atmosphere, recording its chemical composition. There is abundant nitrogen, as on Earth, but also a mix of more exotic chemicals, like methane, benzene, and diacetylene. Nonetheless, many scientists believe the chemistry of Titan's atmosphere mimics that of Earth long ago. If so, Titan may well provide scientists with the equivalent of a time machine to travel back to an era before life first developed on our world. Finally, descending through a last layer of cloud, we see the surface. A close-up view of a tiny portion of the largest unexplored landscape in the solar system. Our brains struggle to interpret what Huygens' eyes reveal. As Huygens spins beneath its drogue chute, descending from an altitude of 9 down to 5 miles, a rich mosaic of light and dark areas is stitched together. Soon cameras zero in on an array of intriguing and mystifying features. Areas of white that may be banks of fog or mist. Bright spots that may be chains of islands or higher elevation peaks amid a level plain. Dark regions where springs of liquid methane instead of water may bubble to the surface, and what may well be a coastline of sorts, where rivers and streams of liquid methane flow down hills of ice to a broad, dark region below. At last, Huygens comes to rest, with more of a splat than a thud or a splash, indicative of a surface with the consistency of wet sand. Its batteries running low, Huygens still remains active for another few hours, recording a surface temperature near 300 degrees below zero Fahrenheit, wafts of methane gas on a light breeze, and a landscape of orange-colored chunks of ice under an orange sky. As Huygens' mission draws to a close, that of Cassini has barely begun. Through at least 2008, Cassini will tour the Saturnian system. Many orbits bring it back for a pass by Titan. For now, it is Titan's turn to provide gravity assists. As a result, Cassini will be carefully directed past many of Saturn's other satellites, while also providing for detailed reconnaissance of Titan itself. Repeated passes by Titan are also used to direct the spacecraft on exotic trips high above Saturn's rings. In each case, dramatic new vistas and discoveries await us. Images of Titan taken on successive passages may be used to make dramatic time-lapse movies to better understand weather systems on this alien world and, perhaps, better understand weather patterns on our own world as well. As Cassini passes behind Titan, scientists will study how radio signals transmitted by the spacecraft are affected by their passage through the satellite's atmosphere. Such studies will help us better understand the composition, density, and pressure of Titan's atmosphere. Cassini also carries a sophisticated radar that can pierce the clouds and accurately map portions of Titan's surface. Already, one such pass has revealed parts of a giant impact crater or basin over 270 miles across, roughly the size of Iowa. Its floor may be flooded with liquid methane or ethane, making it a shallow, very alien lake. Another crater, some 35 miles across, is surrounded by material blasted from inside by an ancient asteroid or comet. Smaller craters would have also been created in the distant past, but may have been obliterated since then, for Titan is a geologically and meteorologically dynamic world. Other Saturnian satellites are coming under close study as well. Cassini's routing calls for several close flights past Enceladus, where giant ice volcanoes or geysers may resurface the landscape and even blast particles far into space to be captured by and replenish Saturn's outer ring. Already, close passes have transformed what previously appeared to be smooth plains on Enceladus into a varied landscape. Here, rope-like ridges up to a half-mile high suggest places where water from the interior has escaped and frozen on the surface. Elsewhere, we see a myriad of large faults, fractures, folds, crevasses, and troughs, all evidence of a dynamic geological history. Cassini has also had its first close look at Iapetus, a satellite with one face as black as asphalt and the other as white as newly fallen snow. Bisecting Iapetus's dark side, Cassini has discovered an incredible ridge of ice that runs over 800 miles along the moon's equator and contains mountains 3 times as high as Everest. Elsewhere on Iapetus, Cassini's cameras capture the aftermath of a huge landslide that partially obliterates the floor of a great basin, ringed by walls of ice over 9 miles high. Later flybys of Iapetus will bring us views up to 100 times sharper. Cassini has also sped past another cratered moon, Dione, where mysterious white streaks discovered by the Voyager spacecraft in the early 1980s are now resolved into vast networks of cliffs of brilliant ice. In time, Cassini will also scan Rhea, another world with mysterious white streaks, to see if these also might be cliffs, or offer some other geological surprise. And Cassini will fly past Tethys, where Ithaca Chasma, an ice canyon 60 miles wide and up to 3 miles deep, cracks this moon nearly pole to pole. Past Mimas, with a crater so large its birth almost shattered this moon to bits. And over potato-shaped Hyperion, home to amazing ice cliffs over 6 miles high. And, of course, Saturn itself is also one of Cassini's prime targets. Cassini is already zeroing in on Saturn's dynamic atmosphere. In visible light, Saturn frequently displays relatively featureless belts and bands of butterscotch, beige, and white. But in infrared light, Cassini's cameras are unveiling an exotic tapestry of swirls, scallops, and spots, telltale signs of a dynamic and turbulent atmosphere with swirling storms and powerful jet streams. This is meteorology on a grand scale. Here, a false color image in the near infrared shows a giant thunderstorm complex larger than the United States. Dubbed the Dragon Storm, it raged for months. A time-lapse movie made during February and March 2004, as Cassini coasted toward Saturn, captures dark storms that sometimes spawn from larger ones, and great white plumes of clouds erupting from deep within Saturn's atmosphere. Cassini is also studying Saturn's magnificent rings with 5 times the clarity of previous spacecraft. The rings are nearly 200,000 miles from edge to edge, yet no more than 100 feet thick. Cassini's cameras spy delicate waves, bands, and wakes within some rings, as well as delicate scalloped edges in others. Tiny satellites that may be little more than loosely packed piles of rubble orbit between or just beyond the rings, and produce such cosmic sculpting using their minute gravitational fields as a tool. Other tiny moons may yet await discovery, their existence suggested by the presence of thin rings recently found within gaps between broader ring systems. The closer we look, the more complex Saturn's rings become. From a distance, the rings look solid. But in reality, they are an enormous blizzard of millions upon millions of pieces of ice that range in size from grains of sand to boulders larger than a house. Each races around Saturn in a separate orbit at speeds up to 50,000 miles per hour. Cassini will focus in on the so-called F-ring that appears to periodically braid and unbraid like a girl's hair. Other orbits will take Cassini on rare excursions high above the rings. Such vantage points will allow Cassini to carefully observe light from selected stars as it blinks on and off through the intervening rings. From such periodic tracings, scientists will gather valuable information on the size distribution of icy chunks and particles within the rings, and how the rings change over time. While this tour phase of Cassini's mission is scheduled to last 4 years, the spacecraft may well remain in good health long thereafter. If so, the mission may be extended to have a closer look at new discoveries encountered along the way, or take on a higher risk assignment beyond the scope of the regular mission. One possibility would be additional close flybys of Titan to improve radar mapping of the surface and perhaps ultimately send the spacecraft on deeper and deeper sojourns through the satellite's atmosphere. Another plan would have the spacecraft make a higher risk passage just outside the rings or even through Cassini's division to obtain even closer scrutiny of these incredible features. Or have Cassini end its life in spectacular fashion by traveling down into the fascinating atmosphere of Saturn itself. Exotic worlds lie at our doorstep. Now they are opening to us like never before, and we can only wonder what new wonders still lie ahead. And in the center of it all, Saturn, framed by rings of glistening ice. Thanks to Cassini-Huygens and the dedicated work of hundreds of scientists and engineers, we are there. And the exploration continues.